In the previous lesson, we worked with two population means with unknown standard deviation. Actually, that is significantly more used than when we know the standard deviation. Very rarely will we know the standard deviation for the population, but we do have to have a method to be able to test it when we do. When we don't know standard deviation, we run t-tests. When we do, we run z-tests. The only difference in the actual calculations is instead of using the sample standard deviation, we're actually going to use the known population standard deviation in both locations, in the standard error and in the test statistic, the z-score itself. We're going to use both standard population standard deviation in both of those locations. But even though we have the formulas, the math formulas to use, I'm not going to actually plug these into the math formulas. You can, if you want, you can try it out. I'm going to use the website Statistics Kingdom, and I'm also going to do this in the TI-84 Plus. Both of those will calculate and do the grunt work for us. But again, it doesn't mean it's going to answer everything on our behalf. It's just going to do the grunt work of the math for us. We still have to figure out what we're testing and which test to use, and we also have to interpret our results and know what they mean. So let's see an example. And in our example, we have two independent groups, and we know the standard deviation for the population. The mean lasting time of two competing floor waxes is to be compared. 20 floors are randomly assigned to test each wax. Both populations have a normal distribution, and the data is right here. For wax number 1, it lasted an average of 3 months, with a population standard deviation of 0.33. The second floor wax lasted on average 2.9 months, with a standard deviation of 0.36. We want to know, does the data indicate that wax 1 is more effective than wax 2? We're going to test it at 5% significance level. Now we need to translate this more effective. If it is more effective, that probably means does it last longer? And lasting longer is just another way of saying greater than. So we want to know if the average for wax 1 is greater than the average lasting time of wax 2. And because of that, this is a one-tailed test. And if mu1 is greater than mu2, that is a right-tailed test. So we need to know that before we go to any website, and really before we hit the calculator, we need to know what type of test we're going to run, a z-test and a right-tailed test. All right, so jumping over to Statistics Kingdom, I have changed it to where I am using a 2 sample z-test calculator. Okay, this is just another test that they have. It's way cool. I do look at my test statistic and see, is that the right test statistic that I want? Yes, it is. Testing parameters. First of all, I'm not running a left-tailed test or a two-tailed test. I'm running a right-tailed test. I also want to make sure that my alpha is set to the appropriate level, which is 5%, 0.05. I'm not worried about outliers. I don't want to exclude them. I'm just going to say go ahead and include them. And I'm not even worried about the effect size right now. We're going to assume the population differences is 0. So the difference between the population mu of the first wax and the population mu of the second wax, we're going to assume there is no difference. Once we have our parameters set up, let's go ahead and enter our sample data. For group 1, I'm going to say this is wax 1. Just to give it some label, and group 2, we'll say that's wax 2. For wax 1, our mean number of months that it lasted was 3. Our number is 20 because 20 floors are randomly assigned to test each wax. And our standard deviation for the population is given of 0.33. I do not care about the sample standard deviation. I know the population deviation, so about the sample standard deviation. Now moving on to group number 2, wax 2, its sample mean number of months that it lasted was 2.9. Sample size again was 20 floors, and its population standard deviation was 0.36. Now that I have all of the data in there, I'm going to calculate the test. Let's scroll down and see our results. Beautiful. It gives us everything we absolutely need. Our p-value equals 0.179, and therefore p is greater than our alpha of 0.05, and therefore we fail to reject H0. We're going to accept H0 is a legitimate hypothesis. But keeping in mind what H0 was. H0 was the mean length of time that wax 1 lasted was less than or equal to the mean time that wax 2 equaled. So mu1 is less than or equal to mu2. But that wasn't our claim. Our claim was that wax 1's mean time was greater than wax 2's mean time. And therefore, we have to say our claim is, we don't have enough evidence to support our claim. Now we can look at effect size. The effect size is small, and therefore we would have to run a test like this to see it. It's not visible, so to speak, to the naked eye. And we can actually say that at this particular level of significance, from the sample data, there's just not sufficient evidence to conclude that the mean time wax 1 lasts longer or more effective than the mean time of wax 2. Now here's the cool part about that. If you are a company and you're doing research about products that you want to use in your company, and these are comparable waxes, but one is twice as expensive as the other, then you would want to use the less expensive wax, right? Save yourself some money. This happens all the time, believe it or not, with food products, because food products will have wax on them to make the food last longer. And so if a company is spending lots and lots of money on this wax, even if it is floor wax, I'm just saying it might be fruit wax, that they would want to save money if it lasts just as long. There's no difference in this case. There's not the sufficient evidence to conclude that the wax time is longer or more effective for the first wax than it is for the second wax. Now let me show you what it looks like doing this on the TI-84. Same problem, but just using the TI-84. I'm going to go to Stat, go to Tests, and I'm going to do a 2-sample Z test. I don't have data, I have stats. So I'm going to change it to stats. My standard deviation population for my wax 1 was 0.33. Standard deviation of the second one is 0.36. My average for the first one was 3, with N being 20. My X2's average was 2.9, and its N was 20. And then I have to figure out the right test to do. Mu1 is greater than mu2, so I want to make sure that I'm on greater than. And I can either graph it or I can calculate it. I'm going to go ahead and draw. My P is equals 0.1799. That is greater than my alpha, and therefore the same result is failed to reject H0. Again, that affects my claim. My claim was HA, and therefore I could say there's not enough evidence to support my claim, or there's not sufficient evidence to support my claim that wax 1 is more effective than wax 2. All right, so I don't normally do this, but I am going to go run through a try it for you. I'm going to plug these in using the TI-84, and we're going to get a solution for this try it. The means of the number of revolutions per minute of 2 competing engines are to be compared. 30 engines are randomly assigned to be tested. Both populations have normal distribution. Our table shows the results. Do the data indicate that engine 2 has a higher RPM than engine 1? And we're going to test at 5% level of significance. Now let me pop over to our TI-84. And again, I am going to run a z-test. So stat, go back to our tests, go to our sample z-test, which is 3. And I'm going to change some values here to the problem set. Okay, for engine number 1, its standard deviation was 50. For engine number 2, its standard deviation was 60. Its average for 1 is 1500 RPM. And we were testing 30 engines. For our average for our second was 1600. Again with 30 engines. And we want to know, do the data indicate that engine 2 is higher RPM than engine 1? Since I put in my engine 1 data first, I have to switch around the language and say, is engine 1 has lower RPM than engine 2? I have to match up who came first, the chicken or the egg. If I want to know if engine 2 has higher RPM, if you switch that, mirror that around, that means engine 1 has lower RPM than engine 2. Otherwise, you got to switch your data around. So I am a less than this time. And I'm not going to draw it. I'm just going to go for calculation. All right. Our P is extremely, extremely small, ridiculously small. And therefore, P is less than alpha, and I reject H0. And if I reject H0, then HA is good. And therefore, I have enough evidence to support my claim that engine 1 has lower RPM than engine 2. And I would just reword that slightly to fit to the actual problem. I have sufficient evidence to say engine 2 has a higher RPM than engine 1. All right, let's pop back into our book and check out our next example. An interested citizen wanted to know if Democratic U.S. senators are older than Republican senators on average. On May 26, 2013, the mean age of randomly selected Republican senators is 61 years and 247 days old, or 61.675 years, with a standard deviation of 10.17 years. The mean age of 30 randomly selected Democratic senators was 61 years, 257 days old, with a standard deviation of 9.55 years. That seems awfully close. I'm probably going to determine that they're not older. But here's what we want to test. Does the data indicate Democratic senators are older than Republican senators on average? We want to test this at a 5% significance level. Now this time I'm going to use the website, and I've split my screen because I need the information up here to be able to fill in the information I need for Statistics Kingdom. First of all, I am testing to see if Democratic senators are older, greater than Republican senators. So if I'm saying mu1 is greater than mu2, then that is a right-tailed test. My alpha is 5%. I'm okay there. And everything else I'm going to leave the same as it is. Now I'm going to go down into my sample data. This time I'm going to say group 1 is Democratic. And group 2 is Republican. For this, it really is going to help me figure out whose data goes where by labeling these. Apparently, I can't talk and type at the same time. All right, for Democratic, their mean age of 30 randomly selected, so we know our N is 30. Their mean age was, I'm going to do the years, 61.704 years with a standard deviation of 9.55. For Republicans, their mean age was 61.675 with 30 Republicans, right? 30 Republicans. And the standard deviation of 10.17 years. It is incredibly important that I get these numbers with the right category. The previous example, I kind of flipped things around because when I put in my data before I really kind of thought about what I was testing, so I had to readjust stuff. Here, I looked at the question and put in my data according to the question. Now let's calculate the test and see our response. Okay, our p-value is 0.4954, meaning p is greater than our alpha because our alpha is 0.05, and our H0 is accepted. Our claim is the Democrats are older than the Republicans. That's our claim. But we're accepting the other thing that we tested, which is H0. And therefore, our claim is bad. H0 is good, where they're less than or equal to, and our claim is bad. We do not have enough evidence to conclude that the mean age of Democratic senators is greater than the mean age of Republican senators. So that's it. All right. So until next time, be seeing ya.